This CFD training package contains 7 different products applying the VOF multiphase model by ANSYS Fluent software. This CFD training package will help you get familiar with professional, industrial, and academic CFD projects in the VOF multiphase area, such as simulating the distillation column tray, mixer tank surface evaporation of falling water droplets, open channel flow, ejectors, oscillatory wave, and also flow in injector CFD simulations. By clicking on the subscribe button, you will be informed about the newest CFD training videos by MR-CFD. Or if you are watching the training video, click on the MR-CFD logo and subscribe.
In this project, we will simulate the distillation column tray two-phase flow process. The meshing of the present model has been done using ANSYS meshing software, and the mesh tab is structured. Under the General Setup tab, you can see different buttons from scales to units. By clicking on check button, you will see that under the Console tab, the Fluent software will start to check your mesh for any errors. By clicking on Display button, a new window will appear, which you can see different parts of your geometry. There are several assumptions taken into account for this project. The first one is that the type of our solver is defined to be pressure-based, since we are dealing with incompressible flows. As for the velocity formulation, we have taken the absolute format, and as for the time study, we have selected the steady time study since we didn't want our results to be a function of time. We have also enabled the gravity, and the amount of gravity is equal to minus 9.81 in z direction. Now, in order to simulate two-phase flow, we double-click on the multiphase button, and in the opened window, under the Model tab, we select and enable the volume of fluid model. Also, you can see that under the number of Eulerian phases, we have defined 2 phases. If you click on the gas inlet boundary, you can see that the type of this boundary is defined to be velocity inlet. By clicking on Edit, a new window will appear in which you can change the settings for this boundary. For example, in the appeared window, you can see that under the Momentum tab, the velocity magnitude defined for this boundary is defined to be equal to 23.35 meters per second. Also, in order to see the settings for different phases of air and water, under the phases you can select from mixture, air, and water. For example, if you select water phase and in the appear window, you can see that the water volume fraction defined for this boundary is equal to 0, which refers to the fact that this boundary is a gas inlet boundary. As for the gas outlet boundary, after clicking on Edit button, the most important thing that we should pay attention to in this window is that the gauge pressure actually is defined to be 0, which means that the fluid flow will exit this boundary to the atmosphere. As for wall boundaries, they all have the same settings, and if you click on Edit, in the appeared window under the Momentum tab, you can see that the stationary wall motion alongside with no slip shear condition is defined for all of the walls. For example, in this project, you can see that a mass flow rate report has been defined on 4 boundaries of gas inlet, gas outlet, liquid inlet, and liquid outlet. After double-clicking on the Residuals button, a new window will appear. In the appeared window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than these criterion, it conveys the meaning that that equation has reached convergence. Now, before proceeding to the next part, we first have to define the volume fraction of water to 1 by clicking on Patch button. After clicking on that button in the appeared window under the phase section, we select water, and after that you can see that the value of 1 has been defined for this phase. After that, by clicking on Domain Solid Zone to Patch, we select our desired zone where we want to patch our new data. After that, by clicking on Patch, our data is transferred to the software. In order to extract 2D contours, we first have to define a plane. In order to do that, we click on Location and then select Plane. After that, in the appear window, we select yes, and in the low left side of the software window, you can see that a new part will appear. In the appeared part, in front of the method section, we select xz plane, and we set the value of z to be equal to 0.2 meters. Now in this velocity contour, you can easily see the velocity distribution of air flow, and you can easily see how the air has entered the computational domain from the lower inlet part. Now in this contour, which is the water volume fraction contour, you can see how the water has entered the computational domain and has accumulated on the tray, and you can see how the water has flowed downward through the holes on the tray. Now finally, in order to extract a 3D contour, all we have to do is to click on volume rendering button and accept the appear window. After that, just like the previous slide, a new part will appear on the low left side of the software window. Again, in front of the variable section, we select, for example, water volume fraction, and then click on apply button. Now in this contour, which is the water volume fraction contour, you can see how the water has entered the computational domain and has accumulated on the tray, and you can see how the water has flowed downward through the holes on the tray. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
In this project, a tank mixer is modeled and the effect of its rotating impeller on the mixing procedure is investigated. In this project, a tank mixer is modeled and the effect of its rotating impeller on the mixing procedure is investigated. The simulation is done using the VOF model for the 3 phases of air, water, and salt. The K-epsilon model is applied for solving the turbulence flow inside the tank, and also the MRF model is used to model the rotation of the impeller that we will mention about them at following. The geometry of this project includes a tank, a mixer consisting of a rod and an impeller. The geometry is designed in the ANSYS design modeler and meshed by ANSYS meshing. The mesh type used for this geometry is unstructured. There are some assumptions considered in this project. The simulation is done using a pressure-based solver, and also the effect of gravity has been taken into account in the y direction. The implicit formulation is more stable than the explicit, and the solution convergence is also easier. The sharp method is used when the interface between the 2 phases is completely clear and the phases do not penetrate at all. The material properties of all phases can be identified in this section. As we are going to simulate the rotation of the impeller in the mixer tank, so the frame motion method has been used. The axis direction is equal to y, as it is obvious. Here we can specify the rotation axis origin, that all are 0. And finally, we set the rotational velocity equal to 10 rounds per minute. This is the interface zone, and the type of boundary condition is set equal to interface. There are 2 separate outlets in this computational domain, as we mentioned before, and both of them, the pressure at the outlets condition is equal to the atmospheric pressure, and since the gauge pressure should be equal to 0. There are a lot of walls in this computational domain containing top wall, wall rotate, wall tank, wall tank of impeller, and so on, and all of them are a stationary wall with no slip. Setting under relaxation factors, we should say that the pressure-based solver uses under relaxation of equations to control the update of computed variables at each iteration. In ANSYS Fluent, the default under relaxation parameters for all variables are set to values that are near optimal for the largest possible number of cases. These values are suitable for many problems, but for some particularly nonlinear problems, for example, some turbulent flows or high Rayleigh number, natural convection problems, it is prudent to reduce the under relaxation factors initially. It is good practice to begin calculation using the default under relaxation factors. If the residuals continue to increase after the first 4 or 5 iterations, you should reduce the under relaxation factors. Occasionally, you may make changes in the under relaxation factors and resume your calculation, only to find that the residuals begin to increase. This often results from increasing the under relaxation factors too much. A cautious approach is to save a data file before making any change to the under relaxation factors, and to give the solution algorithm a few iterations to adjust to the new parameters. Typically, an increase in the under relaxation factors bring about a slight increase in the residuals, but these increases usually disappear as the solution progresses. If the residuals jumped by a few orders of magnitude, you should consider halting the calculation and returning to the last good data file saved. You can use the Residual Monitors dialog box to control the residual information that Fluent software reports. In the equations section, the residual option indicates the name of each variable for which residual information is available. And the monitor indicates whether or not the residuals for each variable are to be monitored. You can toggle monitoring on and off for each variable by turning the corresponding checkbox in the monitor list on or off. The check convergence option indicates whether or not the convergence of each variable is to be monitored. If convergence is being monitored, the solution will stop automatically when each variable meets its specified convergence criterion. You can check convergence only for variables for which you are monitoring residuals. You can toggle convergence checking on and off for each variable by turning the corresponding checkbox in the check convergent list on or off. And finally, the absolute criteria or relative criteria shows the residual value for which the solution of each variable will be considered to be converged. To set this value, manually enter the new value in the corresponding absolute criteria field. And that's it. Set the number of iteration. And here is 270, and just click on the calculate button to start the solution. From the contour section in the graphic of the results, we can display every desired two-dimensional contour on the plane that we have been identified before, that is X content at the middle of the mixer tank. And now we are going to make another plane in the XY plane that the Z constant and is in the middle of the mixer tank. Now we can see the velocity magnitude two-dimensional contour on the other plane of Z equal to 0. Here is the mixture phase. The volume fraction of air is obvious in this contour. And finally, here is the salt volume fraction. The applied settings are recapitulated in the following tables as a review.
In this project, we will simulate the surface evaporation of a falling water droplet. The meshing of the present model is performed by ANSYS meshing software. The mesh type is structured and the face meshing method is used. Also, the element number is equal to 94,800. Now, if you double click on the multiphase button in the appeared window under the models tab, you can see that we have selected the mixture model. Also, we have enabled the slip velocity and implicit body force. Now we have enabled the implicit body force since the main force applied on the droplet is the gravity. Also, under the number of Eulerian phases, you can see that we have selected 3 phases. Next to the forces section, if you click on heat mass reaction section, you can see that a mass transfer mechanism between two phases of water and vapor is defined using a UDF. In order to define that UDF for the software, we click on User Defined Ribbon tab. Now, if you expand the report definitions, you can see that two different reports are defined here. Now, after initializing the software, you can see that the value for water and vapor volume fraction are defined as 0. Now we need to define the position of the droplet for the software. To do that, we click on Domain Ribbon tab. Now in the appeared window under the phase section, we select water and we set the value of volume fraction of water phase to 1 in the defined region. After the initialization process, we double click on the Run Calculations button, and in the appeared window under the Parameters section, you can see the values for number of time steps and time step size and maximum of iteration per time steps. After defining those values as follow, and as you can see in this window, we click on Calculate button and the software will start the simulation process. Now in this contour, which is related to the last time step of our simulation, you can see that the droplet is completely evaporated. And in this contour, you can easily see the velocity distribution inside our computational domain for the mixture. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. In this project, we will simulate the air and water flow inside an open channel. The standard K-omega model is used for solving turbulent flow equation. Also, multiphase VOF model with the use of an open channel setting is activated to simulate two-phase flow of water and air inside the channel. The water enters the channel with a mass flow rate of approximately 60 kilograms per second, and its interaction with the air phase inside the channel is simulated. The geometry of the present model is designed in ANSYS Design Modeler software. Also, by clicking on Report Quality, again in the Console tab, the Fluent software will give you the quality report for your mesh. For example, you can see the maximum aspect ratio of your mesh, maximum orthogonal quality, and etc. After clicking on the Phases tab, underneath the Phases section, you can see the two phases of air and water has been defined here. Also, in order to add a new phase, all you have to do is to click on Add Phase button and then add a new phase from the material you have defined. Now, adding a new material to the software will be defined and explained in the next slides. After clicking on the Viscose button in the appeared window, you can see that we have selected the standard K-omega model. Now, K-omega model has a benefit of better calculating the amount of forces and shear stresses near the walls in comparison to models like K-epsilon. After clicking on Inlet Boundary, you can see that the type of this boundary is defined to be mass flow inlet. Also, by clicking on Edit, a new window will appear in which you can change the settings for this boundary. In the appeared window, under the Multiphase tab, you can see that the option of Open Channel has been enabled. Also, in front of the free surface level, you can see the altitude of the water level entering from this boundary. Now, under the Phase section, if you click on Mixture and select Water, you get to select and define its mass flow rate. Now, as was previously mentioned about the benefits of using a K-omega model over the K-epsilon, you can see that here we have defined a report for the field variable of wall fluxes or wall shear stresses under one of the walls. After double-clicking on the initialization button, a new window will appear showing you different methods of initialization, hybrid and standard. Now, in the standard initialization method, you get to choose the first amounts and values for the first iteration of the simulation progress. These values refers to the values used in the first iteration of the simulation progress, and if you choose the values for each parameter wisely, your simulation progress will finish sooner. It should be mentioned that you can also choose the first values or the initial values by just clicking on the Compute From drop-down list and clicking on one boundary. For example, by clicking on Compute From All Zones, the software will automatically average the values in different zones and boundaries and put those values in the initial values for the software. Now, in this contour, you can easily see the changes of the velocity inside our computational domain for two phases of air and water. Now in this contour you can easily see the changes of the volume fraction of the water phase. Also you can easily see the interface between two phases of water and air. Now after defining the plane, we click on 2D Contours button and then accept the appeared window. Again, on the low left side of the software window, in the appeared part in front of the location, we are going to select our defined plane. And after defining this plane, we are going to select our desired variable, which in this slide we are going to select the water volume fraction again. After that, by clicking on apply, the software will show you the 2D contour on this plane. Again, just like the previous slide, you can see the volume fraction of the water phase here. Also, you can see the interface separating two phases of water and air. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. In this project, we will simulate two-phase flow inside an ejector. In this project, two-phase flow of vapor and liquid ammonia in a two-phase ejector has been simulated by ANSYS Fluent software. The realizable K-epsilon model is used for flow analysis. The VOF multiphase model for two phases of liquid and vapor ammonia has been used to investigate the phase interaction. The energy equation is also activated in this analysis. The liquid ammonia will enter the computational domain through the primary inlet with the pressure of 9 megapascals and a temperature of 393 Kelvin. This flow will induce the vapor ammonia to exit the ejector along with liquid ammonia. The geometry of this model is designed in Gambit software. Now under the Phases tab, you can see the two phases of liquid and vapor ammonia added to the software. Also, in order to add another phase, all you have to do is to click on Add Phase button. And if you have add or defined another material for the software, you can add those material here. Now adding a new material to the software will be explained in next slides. Now in order to add a new material, all you have to do is to right click on Fluid and then select New. After that, in the appeared window, you either can define a new material by defining its properties yourself, or you can click on Fluent Database button and select new material from the list of material available in the Fluent software. After double clicking on the method, you will see that a new window will appear showing you the pressure velocity coupling. Also, you can see that the spatial discretization methods are shown in this window. Also, you can change this discretization into other formats, like you can change them into first order advent and the other options available for each variable under their combo list. And for the simple pressure velocity coupling, the simple algorithm is kind of an iterative solver which uses a relationship between velocity and pressure corrections to enforce mass conservation and to obtain the pressure field. We may also change the under relaxation factors. These factors may be between 0 and 1. Based on the simulation and the project we are doing, we may change these under relaxation factors. But remember that the values set in here are the recommended values for the project, and we highly recommend you to not change these values. After double-clicking on the Residuals button, a new window will appear. In the appeared window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than these criterion, it conveys the meaning that that equation has reached convergence. Now in order to extract contours, all you have to do is to right click on Contours button and then select New. After that, in the appeared window under the Contours of section, you can select for your desired variable, which in this slide we have selected the velocity. After that, under the Surfaces section, you can select your desired surface where you want to see your contour. After that, by clicking on Save or Display button, the software will show you the 2D contour. Now in this contour, you can see the velocity distribution inside our computational domain. In the middle part of our computational domain, you can see the liquid ammonia passing with high velocity due to its high pressure in the inlet section. And along with it, the vapor ammonia will entrain and exit the computational domain with the liquid ammonia. Now in this contour, you can easily see the changes of volume fraction of the liquid, and you can easily see the interfaces separating two phases of liquid and vapor ammonia. So in order to extract the path line or streamlines of the two flow, all you have to do is to right click on path line and then select new. After that, in the appeared window under the release from surfaces, you select two boundaries of primary and secondary inlet. After that, by clicking on save or display button, the software will show you the streamlines. Now in this slide, you can see the streamlines of two phases of liquid and vapor ammonia, and you can see the flow patterns caused by the high velocity liquid ammonia passing in the middle section of our computational domain. Finally, the summary of different settings and setup that we have used in our project is presented to you in the slide. In this project, we will simulate the oscillatory wave and its effect on fin motion. The meshing of the present model was carried out using ANSYS meshing software. The element number is equal to 120,049. In the special region created around the blade, the unstructured mesh is used because it is subject to a dynamic mesh process and is deformed, and therefore this area must be capable of high flexibility against mesh change or remeshing, while in other areas of the model, the mesh is structured. Now in this project, there are several assumptions taken into account. First, the type of our solver is defined to be pressure-based since we are dealing with incompressible flows. As for the velocity formulation, we have selected the absolute formulation, and as for the time study, we have selected transient time study since we are simulating a time progressing phenomenon. Also, our geometry is in 2D, so we have selected the planar 2D space, and you can see here that we have enabled the gravity, and the value of gravity is equal to minus 9.81 in y direction. Now in order to simulate the two phases of air and water, we double click on the multiphase model, and then in the appeared window under the model section we select volume of fluid. Also you can see that we have selected the implicit volume fraction formulation, and under the number of Eulerian phases you can see the value of 2 representing the two phases of air and water. Now in the appeared window, the most important point you should pay attention to is the gauge pressure, which has a value of 0. Now in order to define a wavy motion for the water flow, we have to introduce a user-defined function to the software which makes the deforming zone to have an oscillatory or reciprocating motion. In the appeared window under the smoothing tab, you can see that we have selected the spring Laplace boundary layer method. By clicking on advanced button, you can further change the settings for this method. For example, in the appeared window, you can see that 6 degrees of freedom is defined for rotating flip boundary. Also, you can see the gravitational acceleration applied on this boundary. And another point to be mentioned is that we have enabled the right motion history, and you can see the directory in which the file is saved, and that file shows you the X and Y and theta components of the rotating flap motion. Now under the dynamic mesh zones, if you click on create or edit button, in the appeared window you can select or define dynamic mesh settings for different zones of your geometry. For example, for the outlet deforming zone, under the meshing options, only a smoothing model is enabled since we don't want to have a remesh in this part. Now if you click on the unstructured zone, under the meshing option, you can see that both smoothing and remeshing options are selected. And finally, if you click on wall flap dynamic zone, under the motion attributes, you can see that under the 6 VOF UDF properties, the rotating flap is automatically selected. Also, the center of gravity location for this flap is defined as you can see here. And after that, we enable the 6 VOF option and leave the rest of values to be equal to 0 as you can see in this video. After that, under the variable section, we select the parameter of volume fraction and set the value of it to be equal to 0. After that, we click on the region 0 as we have selected before in the previous slides to be the section where we don't have any water. After that, we click on patch button and the software will apply these settings for us. Now in this slide, you can easily see the volume fraction of the air phase changing inside a computational domain. You also can easily observe the motions and waves produced inside this computational domain due to the reciprocal motion of the left part of our geometry. Now, in order to extract another contour, all you have to do is to change the variable from phases to, for example, the velocity under the contours of section. After that, we click on Save or Display button just like the previous slide, and the software will show us the velocity contour. And now in this slide, you can easily see the velocity distribution inside our computational domain. You can easily observe the velocity has increased in the front section of our vase. And finally, in order to extract a streamline inside our computational domain, we right-click on Pathlines button and then select New. In the appeared window under the Release From section, we select our whole domain as we select the fluid domain and then click on Save or Display button. And now in this slide, in the streamlines contour, you can easily see the streamlines which are related to the waves that are produced inside our computational domain, as there are separate streamlines inside of it. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
And finally, in the last project of the CFD training package, we will simulate a multiphase flow in an injector.
The present problem is going to simulate an injector. The multiphase model, which consists of air and water flows, is used. Water flows through the 3 curved ducts into the reservoir that only has airflow inside its space. The curved structure of the ducts and the cone-shaped state of the air-filled tank distributes the water flow vortices into the injector, thereby discharging the water out of the surrounding of the cylindrical chamber of the ejector. The 3-dimensional geometry of the present model is designed by Design Modeler software. There are 3 ducts with a square cross-section for water flow, a conical shaped area, and a cylindrical chamber. Now, in order to define the 2 phases of air and water for the software, we double-click on the multiphase model, and then in the appeared window, we select Volume of Fluid Model. After that, under the number of Eulerian phases, you can see that we have added 2 phases. In order to add a new material, all you have to do is to right-click on Fluid and then select New. For example, if you click and select the air phase, you can see the mass flow rate defined for this phase is equal to 0. And if you click on the water phase, you can see that the mass flow rate defined for this phase entering this boundary is equal to 0.01 kilograms per second. If you click on the wall boundary and click on Edit, in the appeared window, under the wall motion, you can see that the stationary wall motion along with no slip shear condition is defined for this wall. Now in this 3D contour, which is related to the water volume fraction, you can see that water flows through 3 branches and then enters our cylindrical computational domain and is sprayed through this domain. Now in this 2D contour, you can easily see that the water flow is injected almost in the middle section of our outlet boundary. Now in the streamlines contour, you can easily see how the water has spreaded and injected inside our cylindrical computational domain. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
Obtain the mesh file and also the full training movie by purchasing this product. To benefit from MR-CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.